Well, thank you everybody for coming. I'm really happy that you all did come. And it's Pleasant Street Books on June 28th, and it's the store's been here almost 30 years, and we've had all kinds of customers and also musical events and occasional talks about politics and about any number of subjects in piano recitals. So I'm really happy that Luke decided that he would like to contribute and give a talk. I'm really thrilled about it, actually. And my youngest son Quincy has given a talk about well, too many things to say, but it's more about social issues. And I remember at the time introducing Quincy, I said that I remembered a remark made by his friend from Palestine, Anas Malul, who said that he really, when he first met Quincy, he really liked Quincy because Quincy was someone who, that's a Palestinian expression, he said, Quincy gives a shit. And I thought that in a whole other way, Lukas really also cares deeply about physical reality as well as social reality, and that's very gratifying and necessary. So I'm glad that, and also to want to share the knowledge with other people is. Thank you so much. I'm grateful for that. And Luke grew up in Pomfret and was born outside of Philadelphia, and went to school around here and worked for the NASA on the IBEX project, the Interstellar Boundary Explorer project, in which everybody ought to read something about, and or maybe Luke will say something himself, and has been at the University of Bern in Switzerland, and now is back in the United States. And I'm really grateful and proud to introduce him. Luke Saul.
Thanks so much, Pops, and everybody for coming in. It's great to have a different kind of presentation when I'm used to these specialized conferences and PowerPoint, and so I'd like to make this more of a open source intelligence and open forum, and get feedback. And I'll say a couple more things that some other speakers who have graced this particular forum series: Brian Tokar, Ben Barson, Jack Cole, Teresa Schotz, Michael Barnhart's Shakespeare series here, Fred Ho, Joel Covell, Quincy Saul again, Bruce Gagnon, and there was a world premiere of the mantras here with Luetz and Pops. That's Saul. And yeah, so what I'm gonna do is talk about light and the physics of it, and I'm gonna write a few things about what that means to me, and then we're gonna see what you're the most interested in. Of course, the first thing that comes to my mind is electricity and magnetism. And with the knowledge of these effects, these physical processes, one explains light, one explains propagation of light. And it's not entirely the whole story, though, because if one can understand propagation of pressure in the air and how sound operates based on the equations of gas dynamics, one could, in theory, understand sound. But if someone goes like this, it helps to know what a piano is to understand that. So you need some idea of sources of light in addition to this concept of electricity and magnetism. And a lot of sources of light come into this category of quantum mechanics. These are broad terms, and it's worthwhile to note that we are building a map, a model of the world with this language, and it's not the territory. Don't confuse the map with the territory. Another concept that comes in, also quite related to light, is relativity. And general relativity. And finally, something that you might not hear as much about in a more formal talk about light, but I would like to tell you a little bit about my ideas about it. We have the ether, and in my opinion, it helps very much in understanding all of these above topics to have some idea of what this is. Has anybody, can you raise your hand if you're familiar with this term? Anybody? A few? It's pretty good, right?
I thought it was discredited.
Well, we'll talk about that. We'll talk about that. A lot of theories about these things have also been discredited. What about quantum mechanics? Who is anybody pretty comfortable with the the physics involved? A couple hands, not as many. So perhaps that's the one that's more discredited then. What about electricity and magnetism? Has anybody gone through the exercises in John David Jackson's seminal textbook?
Not recently. We missed that one.
Could any? So I'm definitely going to say a little bit about this, but depending on what, if anybody can present more interest, I'd be glad to go into more details on this. Sorry?
Let's hear about all of them.
All of them. All right. And one theme I'm going to come back to here in this talk is the relationship between sound and light. And these are similar, and it really helps to understand what light is to have some idea of what sound is. And also, another reason I bring this up is because most of the contributors to this this excellent forum have also made a musical offering. So based on this, I'm going to make a little musical offering for you as well. And this is a little bit of a excuse to play my violin for you. But there's another special excuse I have for you, the relation between the violin and electricity. And you probably think I'm a little crazy when I tell you this, but both have been introduced to us by the trees, in particular with the blood of the trees. So now you think I'm really crazy. Here's a little bit of Greek for you. I know there's a Greek scholar in the room, so I ask him to keep quiet for a moment and see if anybody else can read this. Anybody else? We got someone here. Yeah. It's also this word here, electron. So what does it mean? Does anybody know what this word means in Greek?
In Greek? It's not the same thing as it means in English?
No.
It's a tree.
How about familiar with that? Maybe not.
Ancient or modern?
Ancient.
I'm not sure. No.
It actually means amber. It means the tree sap, which has come out, and it's has a natural tendency to collect electrons, in today's parlance, and so you rub it on something and you can get it build up a charge. And as people were learning about charge, this was one of the first objects that one could very simply produce a charge and measure it, see like little flecks of dust would like be attracted to it, and oh, this is what's going on here. And similarly, we have if anyone's ever tried to play a violin with a new bow that hasn't been treated, you're in for a shock. You need a little bit of this rosin.
Electron.
A little electron. So there's a little bit of a stretch, perhaps, but give you something to think about while I play a short song, and then I'll get back to the lecture. Yeah. Any
Sorry,
other
I
questions?
just so by rubbing is that amber?
Well, it will be amber if you give it a lot longer.
And it
Amber
helps
is
to-
typically very, very old and like it becomes a stone, a gemstone.
But it'll build up a charge on the bow. Is that?
And it's actually unrelated.
Oh.
Sorry, no, it actually puts lots of little very small fibers that can grab the string.
Gotcha.
Makes it rough, basically. It's also used by climbers in Fontainebleau to get their fingertips rough so they can grab the rock and pull down. That's getting a little bit off track here. I apologies, but I'm going to play a Bach solo partita in G minor for you.
Great.
Thank you, thank you. Never performed that piece before, so get a chance. So while you're listening, maybe anybody have a preference, something they want to look at first here?
Quantum mechanics.
Yeah, really, start with the beginning.
Yeah.
Okay. I'm not going to get into. I'm not even going to write down Schrodinger's equation for you, because that's really the heart of quantum mechanics. But I'm going to tell you some things that might help you listen to when people start talking about quantum mechanics, and they use. Sometimes they think that there's an issue with light being both a wave and a particle. And the way I visualize that is using my analogy with the sound. You have a note, which is a quantized emitted phonon is another word you can use to describe that. And it's with the piano, it's not very quantized because you can do kind of lightly, and there's different levels, but the frequency is quantized. There's no, unlike the violin, it's you have to play only discrete frequencies. And so basically when you have a source of light, very often it is quantized in a similar way to the way a piano or a harpsichord is even a better example, because then you have only a single volume that you can play as well. So if you have a electron, an atom, it's going to only produce a single type of light, because it can only go between a certain two states. And that's the basic essence of quantum mechanics, is that light emission and light absorption are quantized. It's called the photoelectric effect. And
Could you just define quantized first of all?
oh yes, so quantized just means that there's only certain amounts that are permitted. So you can't play any frequency like I can on the violin. You can play like continual spectrum of different pitches and volumes. Pitches and volumes are continuous. They're not quantized. But if here we're quantized. You can't play between those two notes. So that's one way to get a handle to visualize it. I think that to say a little more, I might need to go into an example of an emission process for light. But it does help to remember that a photon is an emission and an absorption phenomenon. So it's not something that comes flying at you, any more than this note is a note. Well, okay, the note did come flying at you and you heard it, so you could use that language if you want, but it's a little more natural to me to think of the note as being the thing that was struck and also the thing that you heard. But in between, in the air, it's a wave. So it's that's the wave gets it from the source to the ear.
Luke, can I just ask a question?
Yeah, please.
Not too bright. What about mass coronal ejections? How does that relate to
Yeah, coronal mass ejections. Yeah, that's not a quantized behavior. Those things could be, at least as far as I know, it's just they're not that well understood. But these things that come flying off the sun are enormous masses, and accelerated off as they leave, and can strike the earth and cause electrical storms and other bigger effects depending on the size of the coronal mass ejection. You might also be asking about how, like, you see them. You see this material, and this gets into an interesting question. Talking about light, one wants to ask about the sun, as you have just done, and the sun emits a lot of different kinds of light. And you've got quantized sources such as hydrogen atoms on the sun, which are relaxing and emitting notes, if you will, which are referred to as with names like the Lyman series and the Balmer series, describing the frequency of light that these different atoms emerge. One interesting thing about that is that was how helium was discovered. People were looking at the sun and they saw this particular note of frequency of light in the ultraviolet. And what's that? What's doing that? And some bright people said, well, you know what? That's probably some atom that we don't know yet. Let's call it helium. And they were right. It was helium. And they said, let's have a party and fill balloons with this stuff. So yeah, helios is another Greek word, I believe, for the sun. And we're getting into some of the source of the knowledge, if you will. Let me do. There's one nice way to look at light. Should I do that first? Yeah, I'll do that first. This is going to be a little harder because you can't erase on this thing. I'll do it in two parts. So you have a charge, and I'm going to just draw it as a point charge. Just say, let's say it's negative. And then you have, coming out from a charge, defines a charge, in fact, is that it has a field. So other charges nearby will be pulled towards it. And you can draw this field, as it's typically done by putting some lines of force. So if you're here, you're going to be pulled this way. If you're here, you're going to be pulled that way. This is electrostatic arrangement. You may have heard of Coulomb's law, which shows that the force is proportional to the inverse square of the distance. There's other ways to represent this. But what happens if you move this charge suddenly, maybe bump it perhaps with another thing? And so I'm going to draw over here again. Let's do it right here. Let's see if I can do this. It's going to be hard. So this is where the charge used to be, here. And assume that I just sort of shoved it real quick. So far away from this, we're going to be not know yet that I've pushed it here. So you're going to have these field lines which basically are directed to this guy. But inside some, let's do it like this. Perfect circle, huh? Nice. So I'm going to draw these lines in here a little more. These guys still think that the field is coming from here. But in here, we know the field's actually going to where the charge is now. And so what you have is these little kinks in the field lines here. It's not very clear from this picture. I think I'm looks like a spider web after fed him too much alcohol or something. But you can see that there's what was straight lines like we had here now has this kink, and this kink is actually spreading outward at the speed of light. And this is in fact the only way to make light, is you move an electric charge. And there's different ways to move electric charges, many different ways. And for example, if you have your hydrogen atom, the charge is around it in a certain cloud and then perhaps relaxes into a smaller cloud, so you have a motion like that. and many different variations. Higher energy levels have electrons being stretched in lobes, then relaxing down. So you can create with these quantized effects. Of course, another good example of this is in your cell phone. You've got a wire. I'll just tell you and you force current to go up and down it. So you have a charges going back and forth like this at a certain rate, generally in the gigahertz. So about 1 billion times per second. What's that?
When it's charging?
No, while you're talking or while it's just talking to the base, even if you don't expect it to be. It drives a current through an antenna, and so all the charges in that wire go, or in a radio tower. That's 91.3 megahertz. They've got a big wire, and they just drive current through that wire. Goes up and then back down, and it does that 91.3 million times a second, and that's produces light. It comes out copious amounts, and in the radio spectrum. So, talking a little bit about the spectrum, obligatory chart for you here. I think I'm going to do it. Yeah, we'll just do it here. So down here, we're going to start at about 1 hertz. Is anybody familiar with this Hertz unit? HZ? It's this guy Henry Hertz, German guy who was, if you read his Wikipedia page, he was the one who discovered light. So it's kind of funny. What he really discovered was that driving current like this produces light. So he
nationalized in America. He didn't like Germany at all.
Yeah, he came here. Is that true? Yeah.
Well, he lived in America.
Okay. Yeah, I don't know that much about it. So.
Why wouldn't they say that about Newton?
Well, Newton's optics was he did understand a lot about light, but he wasn't aware of the electromagnetic connection. So I'm going to put along this chart here. It's going to go from 1 to 100,000 very quickly. And then we're going to get up to 10 billion. And then on to quadrillion. Is that right? No, just trillion. Just a trillion. And then up here at 10 to the 20. So I don't even know how to say that number. So this is a broad spectrum of numbers across the bottom here. And these are all hertz, which is number of times per second. So if you move your so let's put 91.3 megahertz on here. It's going to be about here. 91.3 megahertz. We're going to get up here, things start to get a little interesting at about 400 times 10 to the 15 to about 800 times 10 to the 15. There's a little region of the spectrum that we call visible. This goes from 400 to 800 or so terahertz. So if you take a little charge and you move it up and down about 5 trillion times a second, you'll be producing visible light. So turns out to be not a very practical way to do it. You're better off finding some atoms that are going to just emit at this frequency in a quantized manner with the photoelectric effect, because that's what goes on in these lights here. You've got a lot of heated atoms that get excited and then they relax, and so the charge pattern changes quickly, emits some light, quantized emission, photon. So here we got infrared, ultraviolet. You got some X-rays here. You got gamma rays way out here, super high frequency. This is all radio. It's a shame to give it such a cursory announcement, and I just like, oh, there's radio waves, all done. But for now, we're gonna move on. What else to say here?
So we don't see most of what's going on. Is that
You don't see most of this. This is the point, Louette. Thank you. Yeah, we see this little bit from 400 to 800 terahertz that we can see. And in fact, what I'm gonna do down here is expand on this for you. Put 400 or so, 800 terahertz, and we're actually going to talk about the eye for a second. There's certain cells in the eye that sense color, if you will, and there's three kinds of them. Three kinds of cones, I believe they're called. Red, green, and blue. And basically, if you have some light that comes in this frequency, it's going to excite some of this kind of the cone cells in your eye. And if you have some light that comes through here in green, it's going to excite this kind. And if you're in the middle, you might excite both of these kinds. And so you got around your eye, you got it's mixes of these that we see as color. So if you have a little bit of this and a little bit of this, you'll be able to tell, like, this is different than light that's just over here. And it's a little bit of a surprise to me at first, to see how really poor the eye is at seeing frequency. We don't that's it. Like, we don't really have good way of identifying frequency. And this can be shown by showing how easy it is to fool the eye with a color TV or LCD screen. You only need 3 frequencies. So you take a little red LED, green LED, blue LED here, and these emitters. With just those 3 emitters, you can show basically all the colors that the eye is capable of seeing. And let's go back to sound for a second. Imagine if you could reproduce the full sound of an orchestra with just 3 notes. Right? It's not going to happen, is it? The ear can measure frequency and tell where you are. The eye doesn't do that. The eye just says, oh, you're excited a little bit here, blue, a little bit of green. It's still quite interesting. Don't get me wrong. I'm not saying like colors are boring. It's quite a different way of looking at frequency space.
So if you're looking at a landscape, especially in May and June, where there's so many different color greens within a landscape, that doesn't seem anything but nuanced to me. That we can see as much color even in one.
Yeah, nuance is a good word for that. It is. It's amazing what you can do with the eye in terms of seeing the differences. I mean, like, some leaf might have certain pigments that allow. We're not used to thinking of it in terms of a spectrum, but if you have let's say some maple leaf might have you shine some sunlight on it, and it's going to have some reflected light that comes off, and maybe it's going to have some light that has a sharp peak here, and maybe it does like this. This is in frequency space now. So it's going to have somebody who does a lot of spectral work will think of color like this. This is what the light from that leaf looks like. Of course, to the eye, it's like, wow, that's a cool looking red, And, but it's not. It doesn't convey. The eye doesn't convey all this information about the different frequencies. It's going to be worth. I could bring this back for you, but it's going to be worth doing the same exact thing now with sound. So this time I'm not going to. By the way, this is pretty phenomenal that you have 20 orders of magnitude of light in frequency. It's there's really nothing like it. And with sound, we don't have that. We have Here's 1 hertz. And so what is it, like 10? About 5 orders of magnitude. But this is, you can actually go up to 100,000 or so and couple sound to air. With water you can go even higher in ultrasonic, but the ear only goes to say 20,000 hertz or so. And this is the interesting thing here. Only 5 orders of magnitude, right? Only 5 orders of magnitude. Guess what? The ear can hear all this. So that's pretty impressive. And it can hear where you are the whole way. So you can identify, I say we're here. You know, this is 440, concert A. And there's another point I'd like to make about the ear while we're here, is that a hearing is logarithmic. And so if you have 440 here, concert A, does anybody know what pitch will be here at 880 hertz? A. Yep. This is the octave. You double the pitch, get the octave. So here's 440 and 880. And then 1760. So if you you notice that I've been drawing these plots logarithmically. And what I mean by that is that it's the same distance here from 1 to 10 as it is between 1,000 and 10,000. And if you think about it, from 1 to 10 minus 1 is 9. So this should be about 9 between these 2 points, right? 10,000 minus 1,000 is 9,000. So if this were a linear plot, this would be 1,000 times bigger than this. But I'm drawing it this way because this is more the way the ear works, more the way we think of it. It's more useful. And if you think about this too, this octave has a range of 440 between these 2 hertz, separating these 2 pitches. And this one has 880 between these 2 pitches. So if sound was linear, like there'd be twice as much to do in this octave as there was in this octave. But to us, it's like it's just another octave. Each one is the same because we're thinking more of a logarithmic. The relative pitch is more important than the actual number of beats per second, of frequency per second. So this is at 8 hertz, we've got lowest organ. I think they call this C minus 1. Is that right? You ever heard that? Low C on the organ. Oh. 8 hertz. That's some low pitch right there. You can also produce this kind of stuff in light with the radio waves, ultra low. I'm not sure exactly what they call it, but if you move your electron back and forth 8 times per second, you're producing radio waves down there. So we've covered the cones of the eye here, the red, green, and blue. And notice this is just not even a single order of magnitude here that the visible light covers. Another interesting thing to note about visible light is that if you look at the atmosphere, and you say the atmosphere is an absorber of light. So light comes in from outside, from the sun, and a lot of it gets absorbed, doesn't reach the Earth. And it turns out, if you look at if you start out with, like, say, some continuous light, all what they call white light, so it's all mix of all frequencies, and you look at what comes through, you see that it's pretty low, not much comes through. But there's a little band here where a lot comes through. And it happens to be, the kind we can see. So, yeah. That's not a coincidence. That's the way the eyes develop to see the light that comes through. Otherwise, they wouldn't be real useful to, identify predators or. Yeah.
The different kinds of eyes, meaning insects and animals, realize a different phenomenon?
Very good question. Yeah, there are a lot of differences. I wish I could tell you more about it, but there's I know like dragonfly eyes are like incredibly fast, and bees and some other insects can register colors that are above our perception, and there are differences. I think in terms of the physics of how it works, it's similar in terms of having the way a cell has portions of it that get excited and stimulates a nerve, but how they see the world is probably quite different. And then spiders have all these eyes, and I'm not sure what they're up to. But that would be a topic for research after this presentation. Sorry, I can't give you a better answer. But certainly these things have been extended. In astronomy, people have tried to look at the stars in all of these things, and you have different advantages and disadvantages. You have much better spatial resolution. If you're looking in radio waves, you can really identify just where you're looking. Where if you're up here in X-ray and gamma ray, it's really difficult. It's hard to tell. It's hard to get good optics. Good. But with these radio waves, they're just phenomenal pointing. It's like down to, what is it, micro arc second resolution?
Yeah, micro arc second. Yeah, with interferometers.
Yeah.
Well, do you mean you can pinpoint the source? Is that what you're saying?
Yeah, you can actually see. You look at a very distant radio source, and you can actually see the fact that your tectonic plate that you're telescoped on is moving, because it's that sensitive to the pointing accuracy. Identify proper motion of stars, like how they're actually moving, which is incredibly slow. Normally, the proper motion of stars, in terms of how they're, not just how they go around with the Earth spinning, but how they might actually just be moving in the galaxy. And they're so far away, and it's extremely difficult to see that. You can register the precession of the equinoxes relatively quickly, which is a process that took generations to identify this effect previously, but with radio astronomy they're able to see it in a night observing. Even I'm not sure if that's true, but it's close to that. Certainly give us our best measurements of precision astrometry, if I'm pronouncing that right. Some of these, there's a lot of unknown territory up here in the X and the gamma ray sources. But now I'm talking a little bit too much about astronomy. Maybe I should cut back a little bit. I've also, I might step back a minute and go into some electromagnetism, if that's all right, unless someone else has a question for me or a direction.
I just wondered if you would talk about a photon at any point.
Oh yeah, well, we'll do, we'll talk a little bit more about photons. These are typically, in this spectrum, anything up here is quantized in the nature of its emission, kind of because it's, well, like I said, if you move your electron, if you can drive a current in a wire in the terahertz range, 1 trillion times per second, up and down, you could make unquantized visible light. But So it's not really photonic. Typically, radio wave sources are not photonic. They're not quantized. They're because you're just driving a current. There's nothing that forces you to a specific frequency or to a specific amplitude.
So they're a wave at that point?
Yeah, well, as you're once you leave the source, as I was saying, if you have a source of light, be it a hydrogen atom or a infrared off of my body or a radio antenna star, it propagates outward as a wave. And this was very well documented by Fresnel. You can, and other, I got a little list of names for you. Huygens, of course. You have refraction. A lot of the effects of light, like a prism, all these effects of light show that is a wave in terms of its propagation, even if it's produced as a photon as source. So it's sort of similar to the, as I was saying, to the phonon. You have a quantized emission of sound, and you've probably seen this famous two-slit experiment. You have a light bulb and two slits in a screen, and then you have a camera over here or a detection plane, and because you have light coming out from these slits like this, it produces a pattern here of light and dark. They call an interference pattern, because these two you have waves from this one and waves from this one, and as you've probably seen in water, if you have at one point you have a crest, another point you have a trough. If they come together, you have flat there. So you have an interference pattern, sort of like you'd see if you dropped two rocks in a pool and you checked out how the water was doing, and some distance away you'd have some points of more light and some points of higher water, some points of lower water. Here it's light and not light. In this case, it's electric field and magnetic field, which are moving up and down as light propagates. So I should, perhaps to explain this better, maybe we should go back to this propagation, the physics of light propagation. But you see here what happens if you have a model of light as being corpuscular. That is, if you think light is like little bullets coming out of the light bulb, then you run into trouble when you get down to a single photon. So you take this, you run your light in such a way that you have just a single electron relaxing in a hydrogen atom. It's like boop, and it emits a single pulse of light. And the thing is that you still see this interference pattern here. So in other words, even though you just let out one photon, it still goes through both slits. And that's if you can see that your propagation is wave-like, it shouldn't really be a surprise, because of course when I play a single note here, it actually went into everybody's ear. But these experiments are what have given us a knowledge of what's going on with how this works, how a single photon can go through both slits. But yeah, I personally don't like to think of it as that. I would like to say, I like to think of it as the photon is the emission. Photon is an emission phenomenon. So the photon is this that happened right here that emitted the light. What goes through the slits is just light. You could say a photon went through the slits if you want. I'm nitpicking a little bit, but it helps me to understand it, that the photon is an emission and an absorption process, not a thing that's like moving through the air. It's just words at that point. I'm not sure I'm being that helpful with that. But I hope maybe that helps a little bit. Any other questions about the two-slit experiment? Are there any other?
What about the difference between the propagation mechanism and sound and light? Does that come into play at all in your analogy?
Yeah, that's a very good question. Yeah, they're not exactly the same. So let me get into to answer that. I'm going to have to show you Maxwell's equations. So, electric people started playing with amber, and they started measuring electric charge, and they came up with Coulomb's law, which I mentioned earlier. And you can also write that as a. I'm just going to write this down. You don't have to. So this says basically the same thing. You've got a charge density. You got an electric field. This is a divergence. Yeah.
What's the delta?
This is it means divergence. It means like how much the field goes out from a point. Then they mostly James Clerk Maxwell was the man basically. It's what some people. I'm not really a historian. Yeah, you like that? Some people say Heaviside did a lot of the work, and I'm not. I'm afraid I can't tell you the detailed history of who did what work, but certainly Maxwell gets a lot of the credit, and he certainly did. In my mind, his equations are basically the height of physics. Like they really describe. We haven't, in terms of light, like they last, and this was the late 1800s. So the magnetic field, on the other hand, is non-divergent. Never has directs it inward to a point or outward. So it's always like parallel lines. So I'll just draw these out for you so you've got like some idea of what this looks like. This would be a dense charge here. Magnetic field, perhaps you have a wire here. The magnetic field will make little circles around it. This is B. B is magnetic field. I'm not sure why that is. Probably a choice of Heaviside or not sure. There's something called Quincy's law, which is that eponymous laws are misappropriated. In other words, an eponymous law is a law named after a person. So like Murphy's law. So there's typically they're named after the wrong person. So another some more vector notation for you. It turns out that one of the early things they noticed is that electric field might, if you change a magnetic field with time, that's what this means, you will create an electric field. And if you change a magnetic field, you change an electric field, you get a magnetic field. Also, you have a current gives you a magnetic field, which is kind of like I drew here. Electric field, magnetic field. So the only reason I'm really showing you these is that these came out of empirical studies. So let's move the amber around, let's measure the field, let's see what happens. And there's lots of different people who wrote these things down in many different ways. Maxwell came along and said, like, this is a nice format to see these things. And he actually didn't use this notation. He used this integral formalism. This is modern notation. But a changing magnetic field creates an electric field. A changing electric field creates a magnetic field. So then you're creating a magnetic field. So back here again, that means you're creating an electric field. You have this like loop. You're going, you make a magnetic field, you make an electric field, you make a magnetic field, you make an electric field. And if you rearrange this, take the in not too complicated a way, you come up with, you can do this for either quantity. You come up with a wave equation. And these mu naught and epsilon naught are constants of how strong the interaction is. Basically just depends on your definition of charge. Like if we're going to charge, you have to if you're going to measure charge, you have to have a unit. And these constants relate to those units, your choice of the unit. So Maxwell was looking at this, he's like, wow, this means like kind of like a wave. Like this looks exactly like sound. In fact, this means that there's some speed and C is a speed, a wave speed traditionally of this quantity. And he plugged these numbers in and he was like, this is like almost the same as the speed of light. That's weird. And this is kind of a serious eureka moment. Like
What's the same as the speed of light?
this speed of the wave that is created by a changing magnetic field, creating electric, creating it's so that's
magnetism is light. Is that what you're saying?
well, yeah. It's if you change a magnetic field, that creates an electric field that creates a magnetic field that propagates out in exactly this format. So this is what's happening here in this picture. We moved a charge, we created a magnetic field, that makes an electric field, makes the magnetic field, and it moves out. Okay. There's let's compare this to sound, because that was Martin's question, actually. With sound, yeah, so far here, by the way, we have not really said what is an electric field. Apart from empirically, we say an electric field is something that makes charge, attracts a charge. But we haven't described what is going on, like, in space that allows these things to exist in space. So that's where people need to look at what this is to come up with that answer. And so we could do that a little bit. It might help to look at sound first, but if you look at let's look at sound. Suppose you have a speaker. Let's draw some speaker here. Incidentally, speakers are done with magnets too, just to confuse you. But it's you've got some sound waves, right, come out, if you will. What happens is you just have a pressure. The pressure here is a little higher. Everywhere in the room, maybe there's like some P0, some pressure everywhere. But then as soon as you push right here, you got like a little bit of extra pressure right here. And then, so you have a gradient of pressure, in other words, a difference in pressure. And so here, the difference in pressure points out. You can write it like this, grad P, if you want to. No, you don't. And it turns out that light is a little different than that. You have, if you have a light bulb here, you also have the similar waves coming out like this. But the electric field actually winds up being like this. It goes like up and down. It's what they call transverse. in a sound is, help me with the words here. Anybody know? the fluctuating quantity is changing along the line of motion.
Longitudinal.
Longitudinal. Thank you. Yeah. And then, but light is transverse. At least if you're looking at E and B, they both they fluctuate in perpendicular. So if you have a light ray, if you will, this is not a good 3D diagram, but you've got some E, some B, and this is the direction that the light's going. But these things, E is going back and forth here, B is going back and forth into the board here.
Question, where does decay in that waveform take place then? Is the decay real or perceived?
That's a great question. Yeah, there's if you're in depends on the medium, first of all, but if there's and the source. If you have the way I've drawn it here, a source like this guy's all emitting light, then you have a natural decay just based on your distance.
Right.
Because your power is going out in all directions. So you make some, just as you would with sound, you have the sound is going out in all directions. If by the time it gets across the street there's almost nothing left. So you don't need to invoke more complicated decay. There is more complicated decay. There's also stuff in the air.
Well, and I don't want to get distracted, but the question is the decay real in that, okay, my sensors can't pick it up, or does it just plain keep going and it gets to a certain point and it just drops on the street, or which is not the case, I don't think, but does it just keep on going and just not able to be perceived anymore?
I think it's the latter. It just keeps going, and eventually you run into the background, like the noise level of
other interference.
Yeah, right. But in theory, goes off forever. So with light, anyway. With sound, you're not going to get out of the atmosphere, but with light, it's you're not going to you'll reach a noise level where no one's going to be able to detect it, but eventually it's going to be blend in with that cosmic microwave background. And there are other more complicated things that happen when you're in media but especially with sound. Light, on the other hand, is perfectly linear. There's no sign of any type of behavior of the medium. In other words, no sign of the ether. So
I don't mean to.
Please.
How does Planck enter into this then?
Yeah, Planck's constant.
Yeah.
Yeah, so Planck's constant enters in when you have let's call this a proton. Put little ears on it, proton. And you've got an electron, and the electron, this will make it a hydrogen atom, just a single electron. And it's kind of let's call it in the lowest energy level. It's kind of all through here is the electron. It sits around it like a hurricane or something, sitting there. And the physics that holds it in there depends on this the fluid. It's described by Schrodinger's equation. And there's different ways it can be visualized, but in the end, it's Planck's constant comes out of the interaction between this electron and this proton, and there's no here's another way that the electron could sit, like this, with these lobes, and the difference in the energies here winds up being, here's the simplest one you can write with Planck's constant, h. This is the frequency, nu. The energy difference between one state in another. It's given by Planck's constant. That's a great question, though. I wish I could give you a better answer. I should go. That's fundamental.
What I've always been fascinated with is the tendency to exist or not. I mean, you know, the box, the shadow box experiment. So, I wanted you to talk about it.
Okay, yeah, well, we could do this Schrodinger's cat kind of thing, because I have my own opinions about that too. There's something that people refer to as non-locality, which I don't really. I think I more agree with Einstein on that topic, that there's not, or even as Schrodinger's example was trying to say with the cat, it's like you don't really need. It's absurd to think that the cat is both alive and dead at the same time. But
yet that's the answer.
Yeah, but to my mind, for example, I just think of a good example. One might be, let's see, where's my daughter? She's over there, either in the kitchen perhaps, or in the living room. And in my mind, I don't actually know, so I have a model where she's in both places in a certain probability.
Is Luna a subatomic phenomenon?
Well, she's got a probability in my mind, because in terms of measuring, I don't know. I only have probabilities. Being a person observing the world, you have probabilities. There's a certain probability that the sun will rise in the morning, right? It's got a lot of nines on it. Right? 99.9999999%. But things are probabilistic. When it comes to making a measurement, you have a probability, and that's how it's the only way you can really cope and understand. And so it's not necessarily about the physics of the particle itself. That's a
But you cross over into a spiritual quality as well.
Perhaps, yeah. How you view the world, yeah. But it doesn't have something to do with this particular example of the electron here. You can do this with anything. You can say, well, what is is the bookshelf really there? Or am I just seeing it? Am I being simulated? There's a lot of interesting questions. I'm not trying to, when I attack these, I don't like these quantum mysticism stuff. And it's not because I don't like mysticism. It's because I think the physics should be about what you can actually understand and talk about modeling the world. There's always room for mysticism. You don't need to, look at Schrodinger's equation to get there, I don't think. Is that, should I go into that a little more? Or,
no, thank you. I didn't want to go.
I want to hear about the ether. About the ether.
Everything insofar as it has to do with light, I think is good as long as we keep it.
Yeah. So there's these nice experiments that Alan Aspect did with light, polarized light, and you can have an atom like this emitting light in both directions, and the light is coupled. So if you know that this one is polarized in this direction, electric field's going back and forth this way, or then this one's going to be polarized in this direction, up and down. So you don't know, you know they're coupled, but you haven't measured them yet. And that's some people have claimed that this is bizarre in that once you measure this, suddenly you know what this one's doing down here. So you have this sort of non-local knowledge of the system. So as soon as you measure this, so as soon as I see my daughter is not in the living room, I know she's in the kitchen, because I know it's coupled. So it's a similar thing. It's not. I think that one of the troubles with the quantum mechanics is that it's so successful, it's amazingly predictive, that a lot of people can talk a lot of other stuff, and it kind of just gets accepted. Perhaps a Sunnet bill that everybody likes, and throw in a little rider at the bottom. It's multiple universes, that's part of quantum mechanics too. Well, you're not going to say you don't agree with quantum mechanics, right? Well, no, I'm not. It's an incredibly successful theory. But does it really require multiple universes? I'm not so sure about that.
Great analogy.
And maybe if you listen to what I just said a minute ago, you can get the same multiple universes with Newton's gravity or with classical mechanics. And you also have similar unpredictability, by the way, with the n-body problem. If you have, in classical mechanics, if you have two objects that can define an orbit, as soon as you throw in a third object in, this system is usually untractable. You can't write down exactly what's going to happen. So you have like this uncertainty develops even before you get down to the level of the atom.
Lucas, the question. Could you please explain us, for instance, in which situations the speed of light is not constant?
Excellent. Okay. So maybe we should get into the so the speed of light, let's see this one here. It's a little bit less than that, but pretty close. It's actually defined into 8 decimal places.
What is it in terms of Planck's constant for Bill?
What's M over S?
Can't do it. Meters per second.
Oh,
Meters per second. So this is in vacuum, and this is actually gets down to a fundamental question, which is, what is extension? So what is distance? So what, there's the Ottaquechee River's right there, starting to rise now in the rain. And why is it not coming right through here and, sweeping us away?
Just wait a little bit.
There's something between us and the river, right? So what is it? What's between us and the river?
Ether?
Space. Ether. You guys have been well primed. Excellent audience. So yeah, space. So what is that? And one of the things Einstein said is that most kids understand very quickly like what is space and what things are far or close by, but it took him a lot longer. And it turns out that this is actually a definition of what is space. And this is the one, if you look up meter in a dictionary, in a modern dictionary, this is what it will tell you. This is what a meter is. A meter is that distance that it takes light to go this far. A foot is 1 light nanosecond. Yeah, just about. Not exactly, but very, very close. Nice reason to use that unit of measure, the foot. You add an
That's
extra.
the only good argument I've heard.
You add an extra foot of cable to your system, you'll have your pulse will arrive a nanosecond later. The light's about 8 light. The sun is about 8 light minutes away. So you can use this light is what defines distance to us. So we mentioned space, and space is a modern word for ether. And a lot of things can happen in space. What kind of properties do we have? What could you have that in space? Anybody think of something that might exist in space? Anything at all?
Matter.
Hit me. Matter. Okay. Yeah, matter. So maybe mass density. Some density at every position in space at every time. But what else might you have in space?
I think that just about covers it.
That's it? Matter? Well, we had some other ones too on the previous table here.
What about time?
What's that?
Time.
Time. Well, time is... You'll have to come back on that one. I have no idea. We got these guys, electric fields, right? They exist in space.
You wouldn't consider them matter?
No. I wouldn't. There's no mass.
Electrons have no mass.
Electrons do, but electric
Fields
fields don't.
But that's not quantified yet.
So there's magnetic fields.
Magnetic fields, electric fields.
Is there sound?
Sound is certainly exists. You can probably describe it with this, with the matter. There's a little more matter here than here, and then a little later time there's more matter here. So it's not sort of a super, it's not a basic to like what is space. It's a little bit more higher level tool for us. Turns out that one other thing that there's a curvature of space that exists in all points of space. There's a metric, which is how gravity, it's a gravitational field, if you will. That's how it was described by general relativity.
So ether is space?
Yeah, that's what I'm saying. Yeah.
I always think of the word ether as from the common, under ether, but this is with an A, and so that's with an E. So what's the origins of?
That's a very good question. Yeah. So maybe I can get some help from the Greek scholar here.
No, I can't help you on that.
Well, typically you've got the some people just use the E spelling these days. In modern parlance, you see it in the newspaper, and people discussing. They'll say his voice crackled in over the ether. What it means is that like you're using radio communications, and that's where the voice comes from. If you're using radio communications, it came in through the ether. And other times people use this word. They'll say, it was lost to the ether. So like maybe you deleted a file, or something just is gone. Yeah. It's often it's off with the sound that you were talking about, Bill. It's no one else is going to measure it anymore.
What does not exist? Yeah.
So yes, something that's not part of this stuff, but just lost in the ether. So those are the common uses of the word today.
Ethereal people.
Ethereal is the word that you hear. Yeah. It's like not of substance. Yeah. And if you think about space, it's not of substance, right? But it is important. It's like everything exists there, and it's hard to people spell it this way. Also, there's the chemical, which you don't want to confuse it with, which is spelled this way.
Right.
So that's one reason to separate it with the ether.
Interesting that you said that there's a dimensional quality, sort of, if that's what you meant.
Yeah.
Having to do with gravitation and stuff like that. But that means ether is specific to Earth as we know it versus space.
Well,
because there isn't necessarily a gravitational issue in...
It could be flat. These things could be zero.
Okay.
This thing could be flat. It could be this unit matrix with zeros and ones here. It could be flat space, no gravity.
Yeah.
But it still is a property of space. So it is a, you could say, it's flat. Space is flat. There's no gravity here, or E is zero. The question of whether you could actually ever get dead zero is another one that we probably don't have to get into, but so what else to say about it? So that's it. Yeah.
I feel like you owe us a little bit of an explanation with the ether, because this is an idea people were talking about, in the 1700s. Pre-Socratics, and then they got discredited in the 60s and 70s.
Well, let's talk about that a little. So
Yeah.
there's a number of difficulties in determining the nature of this stuff, the ether, and there's been a lot of theories about it. There's been sometimes people have thought of it as being something that existed outside of matter, so like maybe there's ether here but not in a rock. Which is, I think, mostly discredited. There's all kinds of... Maxwell had described it ether with like the cellular structure of space. and that's mostly been abandoned as an approach. There's been a lot of, if you read Whittaker's theories of the ether, he lists, it's a 2-volume set of all these different ways people have tried to describe this stuff, and mostly they were all discredited by a few observations. One of them is aberration of starlight. So you see, if the Earth is moving through around the sun, and that motion causes the light of a star to appear in a slightly different place. And if you're describing, you have to be able to, if you have a theory of the ether, it's got to be able to account for this. Light, if you go through water or something, it bends a little bit. So you have to be able to account for that. You have to be able to account for Michelson and Morley experiment, which is one of the most famous ones. And they were trying to find the motion of the ether relative to the Earth. And they made this table, bounced light back and forth. They made a big rotating table. They could turn it. So, if Earth is going this way, it should be a little bit different than when they turn the table. And they found that they were unable to measure their speed. And
no, the divergence was negligible.
Yeah, they were unable to measure a velocity of the ether with respect to their apparatus.
It was so small that they were unable to measure it.
And mostly this was explained by H.A. Lorentz, who was, after Maxwell, I put him right up there. He's the man. And he's the one who came up with the equations of special relativity that Einstein popularized to a great extent. And he described how if you're moving through the ether, you're contracted. Your lengths are contracted, called length contraction. And your clocks are also sped up. And
Lawrence believed in the ether?
Yeah, everybody did. It's just one thing about it is that when Einstein says so much as space has properties, there's an ether. That's general relativity is an ether theory because it describes properties of space. But he also said the ether is superfluous. So when you're doing calculations about where your clocks are going to say, where you need to launch a projectile and hit the enemy, you don't care about the ether. It's superfluous. It's in fact, you can't really measure it at all due to something which is also called gauge invariance, which I could get into a little bit. It's pretty wild. One of the things about the ether they say it's like being in the ocean, like a fish in the ocean. It's not a very good analogy, by the way, but I'm going to say it anyway. Imagine you're a fish. You live in some deep in the ocean. You don't make it up near the surface or near the bottom. You just live there. And somebody says, well, what is the ocean? What are you talking about? It's just your world. You live there. And so it's hard to say to even talk, mention what you're talking about. What do you mean the ocean? So we're in a sort of that situation here with the ether because it's everywhere, and we don't. But it's actually a lot worse than that because the fish, they move, they push against the water. They can feel if there's a chain, water. It is similar, but there's ways that the fish can interact with it. With the ether, it's a lot harder to observe it for a couple of reasons. You've got I've talked about these guys. There's another way to formalize the electric and magnetic field, and that is with potentials, voltage, and something called the magnetic vector potential. And these are, with these 4 quantities, this is a vector, so it's 3 numbers, and this is a single one. You can reproduce these things by saying E is the gradient of the potential, and B is the curl of the magnetic vector potential. And the most common ways to look at how this relates to the ether. All right, let's step back a minute. Fields. Anybody know what a field is? Okay, so let's give an example. A
Veil field.
What's that? Veil field. There you go. So we'll use Veil field. The on Veil field you have grass. Okay, at every point on Veil field you have a density of grass. That is an example of a field. This number, like grass density, you can define it at every point. So at every point you have a quantity defined. And the way it's defined is by averaging like the stuff, the grass. So you take like some circle of a certain size and you count up and you make that, so you create a field by counting and averaging. It's what's called making a moment of a distribution is the language they use for creating a field. So for example, in the room here we have temperature field. Every point in the room there's a temperature. You have a density field. At every point there's a density of oxygen. It happens to be a little higher right here than it is right here. But in order to do that, you have to define a distribution function. In other words, at every point in the room and at every velocity there's a density. And then to make a field, you have to integrate over this. Perhaps it's going too far, but you have, a density in the room is going to be the integral of F over all velocity space. So any velocity, doesn't matter, we don't care how fast the particles are moving, they all count. We're going to add them all together and we're going to come up with a density at that point. So now that we know what fields are, let's go back here. Say what's the electric field? What's the magnetic field? What are we adding up? Like what is it about space that allows us to define these fields? And turns out to be a difficult question. In fact, it's a difficult question just talking about the air in the room. And Boltzmann came along with this stuff, talking about atoms in the air, and he was laughed out of town. There's like, no way, there's just a temperature, buddy. Like, what are you talking about with your atoms? And he went to his grave, no one believed his stuff about atoms in the air. And in fact, to this day, it's still not that useful. If you're building a refrigerator, you want to use ideal gas laws. You want to say PV equals nRT. You've got these constants that define the properties of the air. You're not going to go in and like make a calculation and like. It's unusual that the kinetic theory of gases is used in engineering.
If you're pushing stuff through air, it certainly matters.
It does, yeah. Typically you use the moments though. You use the fields. You use viscosity. You use kurtosis. These various higher moments, averages, which you can choose to define in terms of an underlying ether. For the case of the air, the ether is the atoms. That's the ether for sound, is the atoms of the air. So the ether for light, well, the atoms of space, if you will. So that's the way I like to look at it.
Is ether then? I thought I thought that the accepted belief now is that there is no ether. Are people talking about ether currently?
I think it's better to use the word space. Because no one's going to tell you there's no space. And no one's going to tell you that light doesn't propagate.
So everyone's sort of not talking about it.
It's just the word itself that is shied away from. And when I have written on this topic in scientific publications, I've avoided using that word.
Okay.
You can just use, it doesn't matter. Use whatever word you want.
This is not a question of physics, but do you remember the time before you knew any of this? No, I'm serious because I don't know any of this.
Yeah.
And I've been quite fascinated to see what you do know. And I wonder if you experience the world very differently from the way you used to, and differently from me, and what I might be missing?
That's a great question. Yeah. I didn't know. Certainly all this stuff had to be learned at some point. It is sometimes hard to think back to when you didn't know that.
But they never taught you about ether in the public school system, right?
Oh, but you know, they'll tell you these things, and they exist in empty space. So that's the ether. That's what ether is these guys.
So according to you, light needs something to propagate.
Yeah, it needs space. We're not.
Luke, I guess what I'm after is something more. I would just like to know: is there a certain level, and I would use the word joy, connected to getting up in the morning and seeing something that you see?
Consciousness.
There is and I didn't. A lot of the stuff I didn't realize. You know, I heard about gauge theory and vaguely had some idea of it, but I didn't realize like how much of a conundrum it is. It's like something that I could think about a lot. I can really. It's maybe it's given me more problems with understanding than. Yes.
Okay, so I'm not a physicist. I don't know much about physics.
You probably do.
Maybe not a very smart question, but so I'm wondering: when light travels through space, part of what you said, does it travel through because there is an electromagnetic field, or because it creates its own electromagnetic field as the did you say the changing magnetic field creates an electric field, which changes as it changes, creates a magnetic field, and so on? Does that mean even if it were in flat space, it would still be able to move because even without electromagnetic field? Does that make sense?
A little bit, yeah. It's kind of. I think you're kind of getting to the question of the chicken and egg kind of a scenario. Like, did the light create the fields, or did the fields create the light? I think that's a question of how you would prefer to describe it. I think I see it as light is. That's what light is oscillating fields. There's this another tangent I could go on here. I don't know how much time you guys want to give me, but
tell us what it is.
Tell us what it is.
So we can question you later.
The way you can describe anything in terms of waves, but
finish.
Using Fourier is famous for his description of how any function can be written as a superposition of waves. It turns out that any field, any quantity, any function, you can write it as a sum of sinusoidal functions.
What kind of function?
Sinusoidal, which is perhaps related, but you know, any electric field pattern can be written as a superposition. Any change of pressure in the room can be described as a sum of frequencies, of notes.
They can be expressed, you're saying?
Yeah, you could view it that way if you like. It comes in handy sometimes, depending on what you're trying to do. But I'm not sure it really gets to the heart of your question.
But light can exist. It creates its own existence in some way.
Well, it needs a source. You know, you need to move a charge to have that initial change, which then propagates outward. And as it propagates outward, that's what
through the ether.
Yeah.
So the magnetic field comes before the light, or at the same time as the light?
At the same time. So it's
same time.
Yeah. There's different ways. Even if you have a static field, like if you have let's say just a current running through a wire, and you've got this stationary magnetic field here, then you could say this is light in a way, because you could describe this field as a superposition of waves using Fourier's theorem. You might not think of it as light because it's just sitting there. It's not a single frequency. It's like for example, if
you're defining light as any wave.
Yeah. Well, I'm saying it's if light is any field configuration, really. Electric and magnetic fields, especially ones that propagate, though. That's what light is. You use the word light to describe propagating electromagnetic fluctuations.
There we go.
In fact, in particular, visible ones. Even if you don't like thinking of radio waves as light, then
Luke, then that brings up an interesting phenomenon because, and you've already said it, our experience is only able to experience a sensor response in ourselves of a really narrow field, in a sense. But you just said something a minute ago that stimulated this. That actually any not, I don't know about collision or interacting fields generates essentially light. Okay, so there's all this other light being generated that we don't experience.
yeah.
So you can be sitting in a dark room essentially. There's all kinds of light in that room that we just don't sense.
That's right. Yeah.
I wanted to ask that because that's something that just hit me. Like,
No, that is pretty a remarkable thing the way how there's, one could imagine, moving that dark room somewhere like, between distant galaxies and really get yourself isolated and try to get rid of any type of fluctuation. You could really get down pretty low, but there's probably still something, that little leftover wave from this light right here, might have gone right out there. And some radio waves, a little bit of some early broadcasts from the 50s.
50s isn't early.
they're still saying,
With the evolution of us, why we only have those 3 cones of light, and why is that so narrow? And so if there's all that light out there that we're missing, we've evolved with only this very narrow, these 3, so
It is interesting, huh?
But isn't that what you said? That's the only air that comes into the atmosphere.
Well, it's partially because it's the one.
That's the only There's
the only thing that there's a lot of that around that particular.
But there is the other stuff. We just can't see it.
Yeah.
There's some of the other stuff.
There's some of the other stuff.
But you can see infrared when they make you see it, or X-rays, and that's not as interesting as just what we see naturally.
Yeah.
If you think about it, who wants to see infrared when you can see what we see naturally?
There's already a lot to look at.
Yeah.
Maybe this is just fine.
Unless you lose those 3 cones because of some injury. So
yes.
You would want to see something.
That's true. Yeah, and if you're in Bill's dark room, you're gonna want those infrared goggles. And one thing is that you might enjoy, which is related to this idea of gauge symmetry, is something called the nocturnal doubling hypothesis. Anybody familiar with that?
Say it again.
Nocturnal doubling.
Something at night that makes you night vision.
Well, it happens at night while you sleep. Everything doubles in size.
Oh, right.
This is a thought experiment.
It's a thought experiment. Yeah. And so when you wake up, you're twice as big.
Yeah.
Your meter stick is twice as big. Your car's twice as big. So how do you know? And the answer is that you don't know. And this is part of this what's called gauge symmetry, where you have, in the case of voltage, you only know a difference in voltage. So there's no voltage. We say the ground is 0 because that's convenient. But if you said the ground was 10 million volts, then this we're 10 million and 120 in the wall socket. It's the same. There's no way to tell 0. We can only measure gradients. We can only measure changes in this, which is related to the density of the ether, by the way, voltage. So it's like a pressure. It's like an ether pressure is one way to look at it. There's a number of ways to look at it, but it's it follows the similar type of law where the But you can only tell a difference. You can't, and because our whole concept of what is distance and what is time all depends on this light moving through the ether. If you take the same ether and you say, like, make it half as dense, like spread it out, everything's going to be twice as big, we won't notice.
So there's no base rate for voltage?
No. There's no, you can't measure, you can only sense a difference. So, if some, giant planet came along and had a huge difference, we could say, wow, like maybe we'll call that zero now. But calling the Earth zero makes sense from a practical standpoint, but it doesn't. And this similarly for this magnetic vector potential, which is related to like a flow of ether. So magnetic, it's a if there's this, suppose the ether's flowing through us all at like 1,000,000 miles an hour, nothing changes. So it's kind of part of the reason why it's like maybe you shouldn't even pay any attention to it. It's superfluous, as Einstein said, because it's hard to even. How does it even affect us? It helps me to think about what these things are and what is electricity, what is magnetism.
But is that your personal belief that the ether is going through us just quicker than we can detect?
No, it's just you can't detect no matter what the speed is. You can't. There's no way you detect it. A is B is a curl of A. Magnetic field is a rotational flow of this this vector. But if you can say, let's like suddenly let A equals A plus some 1,000,000 meters per second north. You or any other constant. You don't change this because B is the curl of A. You won't change this. This new A is going to give us the same B.
The Michelson-Morley experiment didn't.
They found nothing, right? Because it doesn't. You can't measure it. That's the thing. Right. As Lorentz pointed out, he's like, oh, actually, guys, you're never going to measure that because
what are your predictions? Do you think it can be measured?
No, I don't. I mean, not with any.
It's like string theory. I mean, just useless.
It might just be useless.
Well, aren't you measuring it every time you see a trough and a crest of a wave?
Well,
because what's waving?
You're measuring a change in it. It's an important distinction.
But it's still being measured. If you see a wave, there's nothing there that's but space, so something's waving.
No, that's true. Yeah, no, it is. You measure a change in it. Just like a voltage, it's not like saying, oh, well, you're saying there's no such thing as voltage. No, there's voltage is very real. If you're at 0 and something else is at 10,000, you're going to get shocked.
It's a change in the phenomenal.
So it's a relative thing. You measure if suddenly if there was if you have a magnet, you can measure that there's a magnet there because there's a difference from this point to this point. But if you add a constant to that whole thing, like then you won't change anything. So it makes it difficult to say, is there a velocity of the ether? A lot of people might say no, there's not, because you can't measure anything that's a constant velocity. So maybe there's no such thing. I can't really argue convincingly that there is such a thing as a constant velocity. But let's go back to our fish in the ocean. Suppose that fish lives in a part of the ocean which is in a big current, all of which is going north. He doesn't really know because doesn't see the bottom of the ocean, doesn't see the thing that we're defining the velocity with respect to, so he can't ever know. It's kind of like this, suppose you're in the Ottaquechee River and you're in a boat. and you jump out and you swim this way for a while, and then you swim back, and you swim this way for 1 minute, you swim this way for 1 minute, and constant, same kind of stroke. You see, like, when you got back to the boat, and you say, well, how fast is the river moving? Well, you can't know that, because how fast the river moves is about the banks of the river, right? So from just this motion of going out and in to the boat, there might as well be no banks at all, so there's no real speed.
But did Mickelson and Morley do them on the different equinoxes? I mean, there's some obvious things you can do, right?
There are, yeah, but the apparatus itself, according to the description of Lorentz, it's going through space, and it's contracted. You have the Lorentz contraction that will always change the effector apparatus will be adjusted so that you won't see anything.
Very convenient.
Very convenient, you might say, yeah. Yeah. That's, what can I say? I mean, that's the formalism of special relativity. So,
Ask another question, or
is this
not?
a good ending point?
Ending question. So thanks for taking us on this journey through the ether, the quantum mechanics, electricity, magnetism, relativity. So this is, I would be happy with either a empirical, technical answer or a mystical one on this one, but it's kind of a Don Juan question. What's the difference between looking and seeing?
Oh, there's a good one.
We're talking about light, because we're talking about different. This is already in the room. People are talking about different kinds of perception, and if we see the ether, if we care about that, do we? Maybe there's another reality that we're not paying attention to with only our 3 light cones. But if we had an ether theory, we might, or I don't know.
You give me a lot to go on there, but I'm not sure where to go with it. You have the. There's certain levels along your processor as you go from the sensor of the eye. You go down the optic nerve, and then you go over to some other part, and then it's like preprocessor. At some point, you have some model at the end that is what you think you're seeing, which is all in your own head, of course. Because they actually say that it's upside down. Right. Have you heard that? The whole world's really the other. Actually, you're seeing it upside down. So I'm not. You're probably asking a little more. But maybe for a nice final statement, I can go. If you're describing the ether as made up of little particles, like you describe the air as being made up of little particles to describe sound, so you describe space as being made up of particles to describe light. And what are those little particles made up of? So you have to keep going and make a new ether. And so you might say that it's ether all the way down.
Very nice, very nice.